Hello everyone. This is Anubhav Nath. Currently, I am doing my PhD at IIT Kanpur in the Department of Chemistry. So, today is the 11th session of our course entitled as Transition Metal Catalyzed Organometallic Chemistry, its principles to applications. Today I have actually devised several problems by going through which you will understand and you will have a grip on the basic concepts regarding the reactivities and the reaction mechanisms of these metal carbonyls and these metal olefin complexes. So we shall start one by one from the slide one, and by going through which you can in the last part of my discussion, you will be able to actually answer or ask the questions if you have any. So we shall start. So the first question. So let me just take out the pointer first. So for the first question is regarding what is the product of the reaction between MnCO5Br, it is pentacarbonyl manganese bromide, and ReCO whole 5 Na. It's a the both of these compounds are actually these metal carbonyls. And the first one, this MnCO5Br, is a well-known compound. It is actually prepared by treating Mn2CO10, that is decacarbonyl dimanganese, with Br2 in CH2 solvent. By oxidative cleavage of that Mn bond, we get that Mn1 compound. It is very popular and is a yellowish orange colored solid. And this ReCO5 whole Na, this is partially a positively charged entity, because this is a negative charged entity because sodium is positive. It's a alkali metal cation. So ReCO whole 5 is a minus, negatively charged. So there is a significant amount of negative charge that is concentrated upon this ReCO whole 5 moiety. This negative charge is well stabilized by the inductive effect of the minus I, or you can say the minus R mesomeric of the, or the inductive effect of this rhenium compound. I have already stated in the previous slides that this rhenium compound, all these metal carbonyl compounds are actually very stable in its low oxidation state, because the metal, if it is an electronically rich situation, or it is having a significant amount of negative charge, then the pi acidic property, the high pi acidic property of this carbonyl moiety will be able to drag the extra electron density from the metal center, and thus by stabilizing its low oxidation state, or you can say the high electron charge density. Same can happen for MnCO5 here also. Here manganese is in class 1 oxidation state, so the low oxidation state or the high electron density is also stabilized by the high pi acidic property of these carbonyl ligands. Thus, if we so here it is, if we can think of this as an RBr moiety, R, where R is the MnCO5 moiety and Br is a very good living group here, and since there is a significant amount of negative charge on this ReCO whole 5 moiety, so it is actually acting as a super nucleophile, because this negative charge actually well stabilized and it is upon the metal center. That's why the negative charge is actually well to get attacked on any suitable fragment. So now what happens, this Re minus is actually goes and attack on this manganese center, and this MnBr bond gets broken and it gets eliminated in the form of a very strong ionic compound and very stable ionic compound, that is sodium bromide. So what happens in this case is MnCO5Br, it reacts with NaReCO whole 5 with concomitant release of this minus Na of this sodium bromide or NaBr. We form this metal compound, this ReCO whole 5 bonded with MnCO whole 5. So thus this metal halo or carbonyl compounds can be treated, can be actually exploited to prepare this metal bonded compound, where the is a heterometallic compound where the metal bond is present. This Re minus moiety is actually able to actually get actually attack on the manganese center. This is classically speaking, this is a classical example of an SN2 reaction or nucleophilic substitution kind of reaction, where this this ReCO minus will attack on the manganese center with release of this bromide ion. So this is the actually mode of an SN2 reaction. A nucleophile attacks on any alkyl bromide or alkyl iodide to produce this nucleophile attack on this R center RNU with release of this Br minus. Same happens in this case of this also, where the nucleophile is nothing but this ReCO whole 5 minus, but the negatively charged metal center is acting as the SN2 nucleophile. So we shall come to the next question now. What is the product when potassium tetrachloroplatinate is treated with ethylene at 60 bar pressure in dilute acyl medium? So this is a very classical example of preparation of Zeise's salt. Zeise itself, you can see, has prepared this classical compound in 1827, and it is one of the very fast organometallic compounds that have been prepared and isolated and characterized fully. So in this case, what happens? This is potassium tetrachloroplatinate is K2PtCl whole 4. Platinum is in plus 2 oxidation state, where two potassium ions are there and fluorochloride ions are there. So it is a very well known potassium platinum 2 compound. When it is treated with ethylene, that is C2H4, it is actually a gas, and at a very high pressure, that is 60 bar pressure. 60 bar is actually 60 times than the atmosphere pressure that you are experiencing. So the solvent here, it is nothing but dilute HCl. So in dilute HCl, when this K2PtCl4 is treated under ethylene pressure of 60 bar, then this compound is prepared. It is KC2H4PtCl3 dot H2O. One H2O comes from the moisture that is present, and the KCl is actually eliminated here from this HCl. In this HCl also, it is dilute HCl, so it has a lot amount of water also. So the water source can preferentially be taken as the HCl aquadilute HCl mixture. So in this case, what happens? We shall go at one by one. The one of the potassium ion is retaining in this moiety, and one other potassium ion is going to capture this chloride here to produce this very stable ionic compound, that is KCl. And in this case, what happens? This the ethylene moiety. Ethylene actually gets bound to this platinum center. With ethylene moiety actually performs an SN2 attack on this platinum, so that one of the chloride ions get eliminated. That chloride minus will be captured by this potassium ion to produce this KCl, and this potassium C2H4 PtCl3 moiety is produced. This is actually a negatively charged moiety, because you know this potassium is a positively charged cation, so this entire moiety is negatively charged. The geometry is actually square planar anode platinum in this compound, where platinum is bound to three chlorine atoms in the plane, and on the opposite side of one of the chloride atoms, this C2H4 moiety is present. This C2H4 plane is actually perpendicular, not parallel with the platinum chlorochlorochloro plane. So that is in the case. In this case, the geometry is actually confirmed from the X-ray crystallography that this C2H4 or this polyphenic moiety double bond, that is actually C double bond C, is perpendicular to the platinum Cl bond system. That is also evident from the density functional theory. It is actually proof from the extra crystallographic structure. What happens in this case when the bond is actually perpendicular, so that the CH2 moiety of the ethylene is actually does experience very less amount of hindrance from the bulky chloride atoms and also from the platinum center. If it is in the perpendicular fashion, then the CH2 moieties actually drag themselves away from the metal center, so resulting in a very less amount of steric hindrance around the platinum center. That's why in this case the olefinic center is actually perpendicular to the platinum chloride plane. Also the water is also there, and as a solvent of crystallization. So firstly, the compound is prepared by boiling PtCl4 in ethanol. This alternative method where this ethanol is taken as a solvent, and tetrachloroplatinum, this platinum plus 4, is treated by boiling it in ethanol. The first preparation was from ethylene, was described by this Barnbaum at 1868. Not this preparation from ethylene was then described. Also in this case, what happens, from Zeise actually prepared this at 1827, and after he prepared it from after even from 40 to 50 years of window, this compound was again prepared from ethylene and described by Barnbaum in 1868. There is also a fact that is actually covered here. Stannous chloride is one of the very famous Lewis acid. So this Lewis acid actually catalyzes the reaction in a very few hours. This reaction, if it takes some if some takes some 18 to 19 hours, but in this case it takes around actually only a few hours, and the pressure required here was 60 bar, but here in presence of this catalyst essential to the pressure actually required is only C2H of C2H4 is only 1 bar. So at atmospheric ethylene pressure, this essential 2 can catalyze the reaction. What happens actually in this case is essential 2 is a very strong Lewis acid, so it actually helps in dragging the one of the chloride atoms from this PtCl4 2 minus moiety, thus prepare essential to actually is actually very efficient in dragging one of the chloride atoms from this PtCl for 2 minus moiety, and thus it actually helps in performing the reaction in a very less amount of time and at a very low pressure. It's actually atmospheric pressure is 1 bar, but the actual preparation procedure, which was first prepared by Zeiss, required 60 bar of ethylene pressure. Coming to the next part of our discussion, it is regarding the prediction of the products of the following reactions. So question 3 actually covers two similar type of questions, where there is ReCO5Cl, it is ReCO5 plus and Cl minus, when it is treated with ethylene in presence of AlCl3. AlCl3 is a very strong Lewis acid, again aluminum trichloride. And the second question is when this compound CpFeCO whole to I, where iron's oxygen state is +2, Cp is by negatively charged, iodine is also negatively charged, and CO whole 2 is there, when it is treated with C2H4, that is again ethylene, in presence of silver tetrafluoroborate AgBF4. What are the products? So one by one we will discuss the answers. So firstly, if we come to the first question, it is regarding this AlCl3 facilitated substitution of Cl minus. So what happens in the first case, this rhenium CO5Cl, it's a very well known compound, carbonyl compound, just like analogous with MnCO5Br. Manganese and rhenium stays in the same group, in the periodic table in transition metal 3D, and first the difference between them is in the principal quantum number, that is 3 and 4. And when it is with ethylene, what happens? So you can see here in the first case, when ethylene is here, ethylene actually attacks on the rhenium center. In rhenium center, the chloride minus actually gets eliminated, but you know that chloride is not a very good living group. That's why the role of AlCl3 comes into picture. AlCl3 is a very strong Lewis acid, which actually helps in capturing this chloride minus ion from this ReCO5 moiety. So actually AlCl3 then produces this AlCl4 minus anion. This AlCl4 minus counter anion is very stable, and it is well incorporated in the product also. So what happens in this case? This C2H4, the ethylene moiety, attacks on the rhenium center with release of this Cl minus, that is facilitated by the presence of this strong Lewis acid, that is AlCl3. So the product here is C2H4 ReCO whole 5 plus and AlCl4 minus. Since this AlCl3 is a, so here instead of AlCl3, several other Lewis acids can also be taken, such as BF3 or BCl3 or FeCl3 or titanium chloride. So these kind of Lewis acids can also be taken to actually facilitate the capture of the Cl minus from this ReCO5 plus moiety. The C2H4 is actually acting as the very strong nucleophile, and this Cl minus is a living group. Since this is not a very good living group, it is a very poor living group. That's why to make it is a better living group, the incorporation of AlCl3 comes into picture. So the product is CO whole 5 Re C2H4 plus AlCl4 minus. The next question is on regarding the treatment of AgBF4. You know, several kind of compounds can be treated, which are actually very good in capturing the halide or abstracting the halide from the moiety. Ag plus is one of the major source, because you know that AgCl, AgBr, AgI, such kind of silver halide complexes have a very low Ksp value. That's why they are very prone to abstract the anion from the any metal or any moiety. That's how they precipitate themselves. They precipitate themselves. So what happens here? This CpFeCO whole 2I. Here you know that is Cp minus or the cyclopentadienyl anion is a very strong sigma donor ligand. That's why the electron density on iron is very well established. That's why when this Ag moiety is actually AgBF4 is taken is incorporated, this Ag plus actually forcefully takes away this I minus. Then in the vacant space, this C2H4 minus can attack, and this compound is prepared. Since this BF4 minus is non-coordinating, then it goes to the negatively the positively charged iron complex. So the product is CpFeCO whole 2 C2H4 plus and BF4 minus with precipitation of this brownish colored silver complex, silver iodide. Preparation of the reaction is not that much easy. That is actually depicted in the slide, because this AgBF4 silver tetrafluoroborate is a very strong oxidizing agent. So AgBF4 should be handled with utmost care. It should not be kept in mind that any oxidation sensitive moiety cannot be present in the reaction center, because this AgBF4 will oxidize it too. So in this case, the reaction mechanism between these two is a bit too different, though the actual procedure is similar. In both the cases, a halide capturing moiety or unit is actually taken. But in this case, I would rather say the SN2 kind of mode is actually operative, because you see here the Cl minus is not actually the the SN1 kind of SN1 kind of mechanism can be operative, because here you can see the Cl minus is a very poor leaving group. So AlCl3 here comes into picture, and this AlCl bond preparation is actually taken, which actually makes this a very good leaving group with interaction with this aluminium center. The C2H4 then attacks on the rhenium center with release of this AlCl4 minus moiety. So preferably it is a midway between SN1 SN2 reaction, where the carbocation or the cationic intermediate presence is not also very much cationic intermediate preparation is not actually can be ejected. And also the SN2 kind of mechanism, the attack nucleophilic attack of this ethylene can also be depicted, because it is not a very strong nucleophile. What happens in this case, this Ag plus actually captures this iodide, and first it prepares the cation, that is CpFeCO whole 2 plus. And then because this AgI has a very low, KSP, or the very low KSP or the solubility product value. So then this AgI first gets precipitated out, and then this C2H4 attacks on the vacant space that is created when release of this iodide, and we prepared this complex CpFeCO whole 2 C2H4 plus and BF4 minus. So I have already stated that the AgBF4 should be handled with utmost care, because it is an oxidizing agent, and we should be careful that no oxidation sensitive moiety is present in the reaction mixture. Now we will come to the next question, that is prediction of the products of the following reactions. The first one is the treatment of FeCO whole 5 when treated with this cyclobutadiene molecule. What is the product at a very high temperature, that is 135 degrees Celsius? The second question is regarding this CpMnCO3. There is a piano stool kind of compound. Cp is on the above plane, and this manganese is there, which is bound to a tripolar stand of this carbonyl or CO. When it is treated with this double bonded CHO under photochemical irradiation, that is H nu, what is the product? So in both the cases, the first one is the thermal ligand substitution, and the second one is the photochemical ligand substitution. So in later cases, you will encounter several these kind of questions, where a thermal condition will produce such kind of reactions, and the photochemical condition will also produce several kind of products. So here we will see on thermal condition what is the product, and on photochemical condition what are the possible products. So in the first case, where it is treated this thermal ligand substitution reaction, where this pentacarbonyl iron pentacarbonyl iron is an 18 electron system. So because these COs are actually 2 electron donors, so 5 COs will donate 10 electrons, and iron is a 4s to 3d6 moiety. There is again an 8 electron species, so 10 plus 8 is 18. When it is treated with 1,3-butadiene, that is a 4 electron donor compound ligand, when it is treated under a butadiene pressure of 20 bar, it is a very high pressure, and also 135 degrees Celsius temperature, that is a thermal condition, is put through. So what are the products? So you will also have to remember the major cases where you have to remember that the compound that you are producing should ideally follow the 18 electron rule. So here the all the CO compounds that is electron donor, so 5 into 2 is 10, and this is a 4 electron donor. So if we have to incorporate this moiety into this iron center, then we have to keep in mind that it is a 4 electron donor, so 4 electrons should also be eliminated from this moiety to keep it in an 18 electron system. It is already 18 electron system, we are actually adding a 4 electron system ligand, so that's why 4 electrons should be eliminated. So 4 electrons can come from 2 CO or 2 carbonyl moieties. So here, so you can see 2 CO molecules are actually eliminated. To ensure the elimination of 2 CO molecules, 20 bar of 1,3-butadiene pressure is actually produced or given, so that under high 1,3-butadiene pressure, the CO molecules can be eliminated from this iron CO5 moiety. So it is remaining with this FeCO whole 3 moiety, which is actually bound to this 4 electron eta 4 1 4 electron donor, that is 1,3-butadiene. This compound was first prepared by Raylan at 1930, the early 90s. This is an 18 electron complex again, because you can see here iron is a the 8 electron system, it's a 4 electron donor, so 8 plus 4 is 12, and 3 COs will total deliver 6 electrons, so 12 plus 6 is 18. So from this 18 electron species, by thermal ligand substitution more procedure at 135 degrees Celsius, and also by this agent of this also by the application of this high pressure of this 1,3-butadiene ligand, we're again producing an 18 electron compound with release of these neutral CO molecules. Since CO is getting eliminated from this reaction mixture, we have to understand the fact that CO is a very poisonous gas. So chemical hood or a well-equipped hood is required to perform such kind of reactions, because CO is very toxic and it can cause severe harm to the persons who are actually carrying out the reaction. So what happens in the second case? The second case is nothing but the example of photochemical ligand substitution. So firstly, in the first case, you have seen that it's the thermal ligand substitution, where these two CO molecules are actually displaced by the action of this thermal condition. In the second, in this case, CpMnCO whole 3, it's a piano stool complex. We will again count electron of this electron, total valence electron of this complex. COs are 2 electron donors, so 3 COs are actually delivering 6 electrons. Manganese is in plus 1 oxidation state because Cp is negatively charged, so manganese is plus 1, so it is a 6 electron system. 6 plus 6 is 12, and this 6 is actually 18. That's why this is an 18 electron system. So when it is treated with this kind of alpha beta unsaturated aldehyde or carbonyl compound under photochemical condition, what is the product? So here, what is the product? This is the product. You can see here also, you can also see this double bond or this olefinic moiety is a 2 electron donor, because this keto bond is actually very much less electronically efficient. So unlike butadiene, it cannot donate to this manganese center. So this only capable center, that is double bonded CHO. You can see that this CHO is a very good pi acceptor moiety also it is attached, since the Cp minus is a very strong sigma donor. So the extra electron density on the manganese center can be stabilized by the pi acidic property of these COs, and also by the pi acidic property of this connected CHO moiety or the aldehydic moiety. It is was first prepared by Fischer in 1960. So here what happens, if H nu is given, so here you can see 3 CO molecules are there. So one of the CO molecules will eliminate itself to accommodate this double bonded CHO compound. It's an alpha beta unsaturated compound. So what happens in this case, this one of the CO molecules get eliminated, and instead of that portion, this double bonded olefinic compound, that is alpha beta unsaturated compound, is then actually bonded to the manganese center. So this is a manganese one center again, which is again 80 electron and 80 electron complex, because instead of a two electron donating ligand CO, only one this double bonded CHO moiety is actually bound. So it is again a 80 electron complex. So this is a classical example of photochemical ligand substitution, where the employment of this H nu, that is the so this so in one of the cases you can see that the photochemical irradiation takes place, where this CpMn CO whole 3 molecule, one of the COs are substituted by the double bond CHO under photochemical irradiation to produce this 18 electron complex, where this double bond is actually bound to the manganese center. The next question is regarding this, given an example of nucleophilic attack on a transitional metal carbonyl olefinic complex. So this nucleophilic attack on this is a very classical example where the transition metal carbonyl olefin complex is taken under consideration, where a nucleophilic attack by a very strong nucleophile can be discussed. So one of the prime examples that I have taken up here is this moiety, where you can see this carbocationic type of ligand, which is a this is a saturated kind of is a carbon it's a hydrocarbon kind of ligand, where this double bond is actually stabilized by this, or this carbocationic is stabilized by this plus I and the hyperconjugative group of this methyl, and also the OMe, the plus R effect or the mesomeric effect of this OMe group. And this compound is actually bound to this FeCO whole 3 tripod. So now when this compound is treated with the presence of a very strong nucleophile, that is potassium cyanide, that is KCN, so what is the product? You can see that is this nucleophilic addition is taking place in regioselective manner and also in stereoselective manner also, that is in the exo orientation. So whenever a plane is considered, the lower back of this plane is actually considered as endo, and the and endo, that is the inside of this double or this ring, and in the outside of the ring, the moiety, the compound is treated as the exo orientation. So here you can see the nucleophile cyanide is bound to the carbon center in an exo fashion. The nucleophilic addition here takes place in a regioselective manner also. This is a pseudo-selection where is exo orientation is taking place. And the regioselection is also that the positively the cyanide, actually here you can see this double bond is two double bonds are here, and there is a plus charge here in the methyl group. The plus charge can be resonance stabilized, and it can take up this position, this mid position, and also in the methoxy position also. But in this case you can see the cyanide attack on the specific methyl bound carbon only, not on the methoxy bound carbon. There is also reason behind that. You can see, because in this case this positively charged carbocation is there, and since the ortho position of this methyl, that is the alpha position from this methyl, is actually well stabilized by the plus R group, that is it is having the highest electron density. That's why the cyanide actually gets repelled from this OMe group by the electronical enrichment of this OMe group. But here in this case, the plus I and the hyperconjugation from methyl is not that much greater. So in this case, what happens? In this case, the cyanide actually preferentially attacks on this position also, and then this positively charged carbocation becomes neutral, and the iron center then bounds to that this or this 1,3-butadiene kind of system. That is actually 1,3-butadiene system. That is a 4 electron donor. You can count the valence electron of this system also. This iron is a zero in, it is entirely a neutral molecule, so iron is in zero oxidation state. So in this zero oxygen, it is as a 8 electron donor. 3 COs will deliver total 6 electrons. So 8 plus 6 is 14. And this is 4 electron donor, 1,3-butadiene kind of ligand. So again, it's a 4 electron donor. So 14 plus 4 is 18. So it is actually an 18 electron donor. The cyanide actually attacks on the exo orientation, not on the endo orientation, because you can see the lower back of this ring is actually covered by this tripod FeCO whole 3. So it is sterically hindered approach if it is the cyanide is approaching on the endo fashion. Rather on the exo fashion, it is actually experiencing a less amount of, or no amount, no a very minute amount of steric hindrance. You have to remember the fact that in most of the cases the endo part is actually statically more demanding. That's why in that case the nucleophilic addition does not take place preferably. So what happens in this case, when endo orientations will be taken up, when there will be significant kind of hydrogen bonding interaction or any other kind of stabilizing effect in the endo fashion, then only the molecule can undergo this endo orientation. You see, when this CO will bound, if it is bound to the endo fashion, and if this NC moiety will have some hydrogen bonding with the ancillary group present here, then it would actually, there would be a 50-50 percentage weightage for the exo product also on the endo product. But here it actually the exclusively the exo product actually forms, because in this case no amount of stabilization factor can be taken into consideration if cyanide would attack on the endo fashion. Rather, cyanide is actually ready to attack on the exo orientation. So that is the case where the regioselective manner and the stereoselective manner comes into picture, and also the why the exo orientation is preferred for the nucleophile to get attack on this center. The next question is regarding this: what happens when this MnCl2, this manganese dichloride, is treated with magnesium butadiene, that is Mg dot 28 THF C4H6 butadiene in atmosphere. It is also in a butadiene atmosphere in presence of PME3. PME is trimethyl phosphine, who is a very strong sigma donor and a weak pi acceptor ligand in THF solvent at a very at 0 degree Celsius temperature. This is a classical reaction where this is a butadiene transfer by magnesium butadiene takes place. So here what happens, you have to actually see the component of the reaction. Here you can see there is a MnCl2. It's a 3D transitional metal halide which is treated with the C4H6 Mg dot 2 THF. So THF is a 2 electron donor. Magnesium's octet is not fulfilled. It's a butadiene C4H6. It's only one butadiene. So you see here manganese octet is not fulfilled because 2 THF will donate total 4 electrons, because 2 THF is a 2 electron donor to the oxygen center, and C4H6 is a 4 electron donor. So 4 plus 4 is actually 8. So thus by treatment of adding it THF, the manganese octet is actually fulfilled, because manganese 2 plus is a D8 system here. So this is a very well known magnesium butadiene actually is a very well known system of transferring capable to transfer this butadiene. Also PME3 is given here to actually make the compound electronically saturated, where the product is actually would be rather unstable. The entire reacts, this 2 electron donor also phosphine moiety. MnCl2 is treated because in from MnCl2 this chloride elimination will take place, and also the reaction is treated in THF condition because extra THF will be there to actually to make the species more stable, and the low temperature is required to increase the selectivity of the reaction. So what happens in this case, this magnesium is actually eliminated in the form of MgCl2, which is a very stable ionic compound. So from this two chloride atoms are eliminated from manganese, so manganese 2 plus is left with nothing now because MgCl2 is already eliminated. So what happens in this case, this PME3 is a very strong sigma tonal ligand. So PME3 comes and gets bound to this manganese center. This is a manganese 0 center because it is already reduced from Mn2 to Mn0. And this cyclobutadiene, this butadiene moiety, 1,3-butadiene C4H6 moiety, then comes into picture and they get bound to this manganese center. Then to actually increase the electron count of this so that it does not get electronically unsaturated. So now what you can actually count the total electron of this species. So what happens in this case, you can see this is the PME 2 electron donor. Both this 1,3-butadiene compounds are 4 electron donors. So 2 plus 2 is 4 plus 4 is 8, 8 plus 2 is 10, and manganese is a D5 4s to 35 system. So it's a 7 electron species. So 10 plus so 4 plus 4 is 8, 8 plus 2 is 10, and 10 plus 7 is 17. So it's a 17 valence electron system, which is actually not, it is also remaining as a coordinatively unsaturated because 18 electron fulfillment has not happened here. This specific example can actually teach us how this manganese butadiene complex can actually transfer the butadiene from it to the manganese, the 3D metal center, and can grab the halide atoms from the itself to actually eliminate it in the form of MgCl2, which is a very stable ionic compound. Pme3 actually comes to actually stable the zero center. Here you have to note the fact that it's a Mn0 system, and no, and these olefinic moieties are not very good pi acceptor. So the entire pi acceptor property is actually depending upon this phosphine, that is Pme3. So instead of phosphine, if this Pme3 phosphine, we can actually take up several other phosphines also that are actually capable of stabilizing the low oxygen state, that is the high electron density on the manganese center. So basically manganese zero system. So here if we rather say we have to take the PF3 or PCl3 kind of system, then it would be the molecule would be rather more stable. This compound was prepared by Rayford in 1982. So then actually he can not actually we would actually rather can take up this call on this varying this kind of phosphine. From PME3 we can go to PPH3 or PF3 or PCl3 or POME whole 3. Such kind of compound can also be treated upon, so that we can get more stable version of this specific example. The next question is regarding this what happens when when cobalt is treated with ethylene gas in presence of potassium metal at minus 20 degrees Celsius. So, firstly, this is a very popular question on reductive cleavage of any metallocene. This metallocene is a cobaltocene, that is cobalt Cp2. Cobalt is in plus 2 oxygen state. Cobalt is a 4s2 3d7 system. So, cobaltocene, a cobalt 2 plus is there. So, it's a 7 electron system. And these CPs are actually 6 electron donors. So, 6 plus 6 is 12, and 12 plus 7 is 19. So, it's a 19 electron system. So this molecule is a specific example of a electronically oversaturated system. Since both of this Cp minus are actually covering 3 coordination sites around the cobalt center, that's why in both it is actually all the 6 sites are actually occupied. So this cobaltocene is electronically oversaturated but coordinatively saturated. So what happens when this compound is treated with this reducing agent as potassium in ethylene pressure at a very low temperature, that is minus 20 degrees Celsius. So you can see what happens in this case. One of the Cp minus is lost from the moiety, and instead of that, two ethylene moieties are actually bound to the cobalt center. So what can be the possible mechanism of such reaction? So here you can see there is a cobalt 2 plus, and we are actually treating it with a potassium, that is a very well known reducing agent. Instead of potassium, they are actually treating with potassium C8, it's KC8, potassium graphite, because handling the metallic potassium is not a very good idea, because it is very much moisture and air sensitive and explosive. But KC8 is a very well known compound. So what happens in this case, this potassium actually is a very strong reducing agent, and you see this cobaltocene is a 19 electron system. So it is a very strong oxidizing agent, because it has always the tendency to keep down it is to come to the 18 electron system. So from 18 19 electron it should come to the 18 electron system. So it is a very strong oxidizing agent. So what happens, the reaction between a reducing agent and this potassium is a very strong reducing agent, and this cobaltocene is a very strong oxidizing agent, because it is 19 electron system, and it has always the tendency to from 19 to drag down to the 18 electron system, so that it can reduce itself and it can oxidize the other species. So this is a combination of a very strong reducing agent and a very good oxidizing agent. So what happens when this redox reaction takes place, this KCP is actually get eliminated. So Cp minus is actually taken up by this potassium gets oxidized to K plus, and see this COCP, and this cobalt drags down to the COCP minus. So what happens in this case, this K plus actually gets eliminated from the species as KCP.
I didn't catch that. Could you try again?
This KCP. So GPK is a very well-known solid, that is just like an analogous of this NaCP, because potassium is actually it's a reducing agent, and if it reduces this 19 electron system to 18 electron system, then it goes to a potassium plus. From potassium 0 it will go to potassium plus, and this one of the Cp minus which is bound to this cobaltocene will be captured by this potassium plus, and it will eliminate itself in minus at as KCP. the very low temperature minus 220 Celsius, the cryogenic conditions are required because to increase the selectivity of the reaction. So when this CP is eliminated, so three vacant spaces are actually available for cobalt now. So what happens in this case, since extra ethylene is actually produced given in the as pressure, then two ethylene moieties will be bound to the cobaltocene. Now what happens, it is a +1 oxidation state, so cobalt is a D8 electron now. So this 8 plus 6 is 14, and instead of this 6 electron, it will be now going to take up the 2 electrons. So 2 plus 2 is 4 from the two ethylene moieties. So 8 plus 4 is 12, plus 6 from the Cp minus moiety is 18 electron. So from 18 electron system we are going to an 18 electron system. The specific compound is treated used in transferring the half sandwich unit, that is CpCO. You can see there's a CpCO is the half sandwich unit, because this cobaltocene is actually sandwiched, cobalt is sandwiched between two Cp. Since one of the Cp's are eliminated, so this CpCO is actually termed as the half sandwich. So this molecule is actually treated as using as a half sandwich. And this transferring of this half sandwich is taking place when this ethylene extra ethylene pressure is there. So with two ethylene moieties having total 4 electrons will be available to get bound to the cobalt 1 center. So from cobalt 2 we are going to cobalt 1, and from potassium 0 we are going to potassium plus. So that is a typical example of a redox reaction where the reductive cleavage of the metallocene by the effect of this alkali metal takes place. So coming to the next example, what is the product when this RHCl3 is reacted with C2H4 gas, that is ethylene gas again, in ethanol water mixture. So this is a very well known procedure where this metal olefin bond is compounds having metal olefin bond is prepared. So here the is a bridging compound that is prepared here. The typical procedure actually follows as such, when the metal salt should be taken with excess olefin amount, that is the excess amount of olefin pressure is taken, and reducing agent is also there. Here the olefin itself, it's the reducing agent. Here the ethanol has some also properties to act as a reducing agent, because it can have some property in oxidizing itself to corresponding aldehyde, that is acetaldehyde. So what happens in this case is RHCl3 is rhodium plus 3 compound which is treated with this ethylene, that is C2H4. The compound C2H4 is taken in an excess amount, so it is also is a binding agent also, and also as the reducing agent. The solvent here is the ethanol water mixture. So what is the product of the reaction? So in this case what happens, this rhodium 1 center is 3 center is there, and now this rhodium 3 center will be coming to the next form, that is rhodium 1. We know that is instead of rhodium 2, rhodium 1 is one of the most stable configuration of rhodium. So in this case these two rhodium centers can come into picture with this Cl bind bridging. So two rhodiums will retain these two Cl, and other Cl minus will be eliminated in this form, and the C2H4 is actually coming into picture, and the C2H4 will get bound to the rhodium 1 center. You see, because these two rhodiums are there and two chloride atoms are there, so 2x minus 2 is 0. It's an electronically neutral system, and 2x is equal to plus 2, so x is plus 1. So both the rhodiums is actually in its plus 1 oxidation state. So from plus 3 we are going to plus 1, and this ethanol water mixture is taken as the solvent. Here you can actually count the total valence electron of the system. So here you can see this is a rhodium 1 system. Rhodium 1 is a 4 is a S2 S2d7 moiety. So 1 is an 8 electron system. This all the olefins are 2 electron donor, and this chloride has also chloride bridgings are actually 4 electron donors. So 4 plus 4 is 8, and 8 plus 8 is 16. So 16 plus 8 is counting towards 24 electrons, and 4 olefinic moieties are there, who all of each of which are 2 electron donors. So 4 into 2 is 8. So 24 plus 8 is 32. So two olefins, two metal centers are there, and each of them are actually have total 2 metal centers will be experiencing total valence electron count of 32. So each metal center will be experiencing valence electron count of 16. You know, such square planar geometry around the rhodium center are actually stabilized by the square planar geometry around the metal center. So thus from this RHCl3 we are actually producing this bridging, chloro bridging if we can take up this system as two fragments, and this RHCl three olefinic moieties, and this RACL and three olefinic moieties. So all of which are actually 16 electrons actually clapped to each other by the effect of these chloride bridges to produce this 32 electoral valence electron count system. So this RH3 is actually reduced by excess amount of olefin. So the C2H4 pressure, such a high pressure of 30 bar is required to carry out this specific reaction. Now we shall come to the last question of this discussion. What is comparing the different olefinic IR staging frequencies with respect to free ethylene in various complexes? Now we have actually taken up several examples here, and we are actually going go through each of these to see how this C2H4 bound, this olefinic metal olefinic kind of systems are actually having these different olefinic IR CC stitching frequencies. This A system nothing but a C2H4, and we abbreviated this ethylene as A in each of the following species. So six kind of such species are there, and one is the free ethylene moiety. So here you can see in all of these, first one is the A2AgBF4, which is having a IR setting frequency 1584. The next one, AFeCO whole 4, is having the value 1551. The next one, that is A2ReCO whole 4 plus PF6 minus, is having this new in 1539. The next compound, APDCl2 whole 2, is having the new as 1525. The CpMnCO whole 2A is having the new as 1508. And the next one is the IC salt that I have discussed much earlier with this KPTCl3A dot H2O is having the setting frequency in the range 1516. And this last compound is nothing but this free ethylene, that is 1623, which is the highest among all the corresponding species. So what can be the possible reason, and how we will substantiate that how this trend is actually happening? So let's come to the first case. What happens in this case is a silver 1 moiety, that is because the BF4 is a negatively charged, and all the cases A, that is E2H4, is a neutral. So it is C2H4 whole to Ag, but Ag is linearly bound between two. The silver is linearly bound by two olefinic moieties, that is the ethylene. So in this case, you can see the highest one is actually seen in the 1623 centimeter inverse, that is in case of free ethylene. But in all the cases, in the metal bound cases, the value is actually dropped down from the free ethylene moiety. That is can be substantiated in this case. In the first case, what happens? This Ag plus is bound to these two ethylene moieties in a linear fashion. So whenever an Ag plus is there, Ag plus actually is in both the cases. You have to remember, whenever an ethylene or an olefin is bound to the metal center, it will donate the extra electron density to the metal center. The metal will back donate the extra from the sigma, from the pi, from the pi, from the sigma, that is a loop, that is a homo of, there is a pi homo, and from the metal center the back donation will also take place to the pi star lumo. In both the cases, whether it is a front donation from the ligand to metal, or in the back donation from the metal to ligand, in both the cases the bond order of the CC, the olefinic double bond, will actually drop down, so that there will be a decrement in the IR stretching frequency of this C double bond C bond. So in each of the cases, whenever the ethylene is actually bound to the any of the metal atom, the value of the IR stretching frequency is dropped from the corresponding free ethylene moiety. Now we shall have to determine why the variation is there. In the first case, when Ag plus is there, ethylene will donate the electron density pi homo to the Ag plus. Ag plus will back donate the electron to the system, and thus the very decrement of the from 1623. There is a decrement in the new CC. What happens in the next case? It's the Ag plus center. It's the cationic center, which is Ag plus state. In this case, iron is in zero oxidation state, so the extra electron density on the iron center is more. That is actually also well stabilized by the stabilized by the CO molecule, that is a pi acidic ligand. So the iron zero center will be more efficient in back donating the electron to the ethylene. That's how in case of when the back donation is more, the decrement in the new CC will be more. So it is 1551. What happens in this case is the A2 rhenium CO 4 PF6. So what happens in this case? This is a rhenium CO whole 4. You can see rhenium is in plus 1 state also here, not like Ag plus. But here happens, you can see that the value is even dropped down. What happens in this case? The CO4 is extra. So there are two ethylene moieties are there. So the extra electron density on the rhenium center is more, though it is in a plus 1 oxidation state. So this rhenium center will also back donate the electron to the ethylene. Since CO molecules are there and COs are also pi acidic in properties, so there will be a competition between the CO and the ethylene. Those CO molecules are have even high pi acidic, have very high pi acidic nature. So in each of the cases, ethylene moieties will get dominated over by the CO molecules. So here the value is even less. In case of this APDCl2 whole 2 moiety, you can see there are no CO molecules are there. So in this case, the extra electron density on a palladium center will be back donated to the ethylene moieties also. So that's why in this case the value is even lower. In case of CpMnCO whole 2a, so in this case Cp minus is a very strong sigma donor ligand, so that will increase the electron density on the manganese 1 center. So the manganese electron density will be very much high in case of this fifth species, that is CpMnCO whole 2a. So this manganese 1 will again back donate the electron to the ethylene more. So that's why in this case 1500, it is the lowest among all these species is actually observed in this case. In case of isis salt, it is not the case, because in the isis salt you can see, though the platinum is in minus, is negatively charged, you can see that in this case three chloride atoms are there, which are actually not very good biacidic ligand. They're actually a sigma bonded ligand. So they will also drag the electron density from the platinum center with the aid of their minus I effect. So in this case, what happens? The extra electron density is back donation from the platinum center to the ethylene center is not that much high, just like the previous system. That's why it is a slight increment in this case. From 1508, we're actually observing 1516. So in the last case, where there is no such back donation taking place from the pi homo or in the sigma star pi star lumo, the value is highest in case of free ethylene, that is 1623. So this is the list, guys. So in this case, you can see the several examples are actually taken up to actually substantiate between the relative IR olefinic stitching frequencies with respect to free ethylene in various organometallic complexes. So now with this is the end of the slide. Now you can ask for any questions if you have any doubts on any of the slides. হয়ে আছে মিউট করে দিচ্ছি
পাঁচ পেয়েছি অবশ্য ধরে আটকে রেখেছি পড়াচ্ছে কি হচ্ছে মুখ করছে তো এটা কি আপলোড করবে ইউটিউবে? কোথায় যাবে? ক্লাস শুনবে না। তো কি বলি, টপিকের ছবি আছে কোন টপিকটা? মাকে পাঠিয়ে এই তো কাকিমা কাকে পাঠাতে হলো, পাঠিয়ে দিয়েছি তো। আবার টপিকটা যেটা পালপাড়াকে দেওয়া আছে দেখিস নি? পালপাড়াকে কিসের জন্য? আশ্রয় তো পালপাড়া কিসে বিরিয়ানি মানে সব কিছুতে আহ্বান থেকে আশ্রয়। আহ্বানটা কি? সংগঠন। এই সংগঠনের বুধমানে নিজের প্রাইস দেওয়ার অকাত নেই, তোকে প্রাইস নিজের নাম নাইলঙ্গা থেকে যেটা 5 টাকা দাঁড়াবে সব জায়গায় নাকি বারোয়ারি মাঠ ফার্স্ট হয়েছে লাইটে প্যান্ডেলে ঠাকুর অল ওভার সেকেন্ড
এই সমস্ত আগমার থেকে নেয় আগমার থেকে নিয়ে নেন
মা দেয় প্রাইসটা দাদু আর ঠাকুমার স্মৃতি উদ্দেশ্যে বাবা দেয় মা দেয়
আচ্ছা আচ্ছা
জীবনে কাউকেই বলে না যে অর্জুন সিংকে ডাকি অর্জুন সিং আর প্রাইসটা তুলে দেয় বুঝলো এটা ব্যাপার আছে। বিজয় বাবা ভালো বলা বিজয় এদিক ওদিক ট্যাগ করে
মজা ওর লাইন আর মজা
ও ক্যান ইউজ করে না পাবলিক পেন ইউজ করে আর রোলার দিয়ে করে দেখেছি না ট্যাগ করতে দেখেছি ক্যান ইউজ করতে কিন্তু এখন নাম নেই